Now for something very, very different. Up until this point, we've been talking about forces, electric forces that are being applied by one charge onto another. And so specifically when we talk about forces, again, we're not talking about forces between charges. We're talking about the forces on a charge due to another charge, maybe two other charges or three other charges. Regardless, the question remains, what is the mechanism of that force? What is the way in which a charge can exert a force onto another charge at a distance? Maybe one way that I can ask this question is, if I have this charge here and another charge here, let's make this one positive, we're going to make this one positive. And so this charge is feeling a force due to this one. So this fist here is a positive charge, this fist here is a positive charge, and this one is repulsed by this one. It wants to move in that direction. The question is, if I take this charge away, so it's gone now, is there anything here? Is there anything happening in this empty space due to this charge? Think about it. Think about it. If I have a charge here and there's empty space around it, is there anything there that eventually, if I take a force and I put it into the space around this other one, now this one feels a force, this one feels a repulsive force in that direction? What is the mechanism of the force? And if there isn't another charge there to feel the force, is there anything there? If a tree falls in the forest, does anyone hear it? The answer is yes. Oh, no, wait, that's the wrong question. If a tree falls in the forest and no one's there to hear it, does it make a sound? That's it. That's it. And the answer is yes, it does make a sound. And yes, this charge here, even if there are no other charges around it to feel the force, is doing something. What is it doing? It's creating an electric field. It's creating an electric field. And in fact, I am going to show you that the electric field is the more fundamental concept in comparison to the electric force. The electric force only exists because of the field. It's the electric field that surrounds each and every charge that is the mechanism by which electric force manifests itself in another charge. And so really, if I was teaching the idea of forces from scratch, and you didn't even know what a force was, I would actually teach the field first. If you don't know what a field was and you didn't know what a force was, I would teach you what a field is first and then teach you what a force is. The only reason we, as physics professors in first year, teach the electric force first is because you already know so much about forces. But when we do the same thing for magnetism, when we talk about the magnetic force, I will actually talk about the magnetic field first, because after a week or so of doing this stuff, you will understand what fields are. And it's the field that is the more fundamental concept here. And so let's write some of this stuff down. Basically, what are we saying? Up until now, charges are directly exerting forces onto each other. That's what we've assumed. Whether we've said it out loud or not doesn't really matter. But up until now, charges are directly exerting forces onto each other. That's what we've assumed. That's what I've implied without actually having said it. And it's not how we want to think about the concept of force. There are problems associated with assuming that it is directly applying the force, despite not being, they're not touching or anything like that. So it's a direct force at a distance. But our problems include answering the question, what is the mechanism of the electric force? What is the mechanism that the electric force is transmitted? How does the other charge know there's an electric force there and how strong the electric force is and how it gets weaker as we move away from it and all of that kind of stuff? What is the mechanism of the electric force? And so this is essentially action at a distance. And we've just accepted it up until this point that action at a distance was fine. But now we want to explore that idea a little bit more and try to think about the concept of the tree falling in the forest, or in the case of charges, if we have a lone charge, that is a charge by itself, does it do anything? So it's just sitting there, floating in space, not moving. There's nothing else near it. Is it doing anything? Can we quantify any property of it that allows us to not only describe it, but to then use that property to calculate force? And the answer is yes. And so this isn't a theoretical, philosophical question, because the tree thing, I mean, the answer is nobody knows, right? Nobody knows if no one's there to hear it. But in this case, what I'm telling you instead is that we're going to resolve these problems. We're going to resolve this mechanism of forces. We're going to resolve the question of whether a charge is doing anything to the space around it by saying yes, in fact, the fields is the answer to all of these questions. So our resolution to these problems is, let's make it an equal sign, fields. And fields are a class of fields have both a physical and a mathematical definition. And we're going to learn both of them, but specifically what we're talking about to answer this question is the electric field. It's the electric field for us that is going to prove the answer to what surrounds a lone charge. And so basically, I want us to start to rethink about the way that force is applied. So instead of just thinking, oh, I've got two charges, this one feels a force this way because of this one, I want you to think about this charge and what is happening to this charge. This charge is creating an electric field around it in all space. In three-dimensional space, it has an electric field around it. Now what I'm doing is saying, okay, if I take a charge and I put it into the electric field, and in this space here, I know how strong the electric field is, and I put a charge there, I can calculate the force on this object. I know the direction and the magnitude of the force on this charge because it's in the electric field. And that electric field permeates all space, all space. It's stronger closer to our charge. And by the way, this charge, it's got an electric field as well. And how do those electric fields interact with each other? We'll talk about those things in due time. But right now, I just want us to adjust our thinking about what forces are, what the electric force specifically is. The electric force, for now on, is the measurement, the manifestation of force due to the electric field. So the force is what happens when a charged particle goes into an electric field. Where did the electric field come from? The electric field came from the other charges that are there. And that electric field is going to go out in all directions in three-dimensional space, forever. But the farther you get away from the charge, the electric field gets weaker and weaker and weaker and essentially goes to zero if you're far enough away from it. And we'll see all that in due time, but let's write it like this. If we have two charges, one charge is the source of the field, and the other charge experiences the field. Interesting. If we have two charges, they feel a force due to the other's electric field. Doesn't matter which one you pick. You want to talk about this one? Sure, we'll talk about this one. It's feeling a force as well. It's feeling a force because it feels the electric field due to this charge right here. All right. So to really understand this concept, we need to understand a bit more about fields in general. And so let's talk about fields. And the first type of field we want to talk about is a mathematical field, because a mathematical field in some ways is the easiest to understand because it has no physical meaning. It's just a bunch of numbers, and a bunch of numbers can be quite easy to understand. So in math, a field is a function. And we can call that function f. So it just means it's some equation, right? It's some equation, but it's dependent on x, y, and z. What that means is that that function, f at x, y, z, describes some number for every place in the x, y, z axis. So this is a three-dimensional field, and it gives us a value everywhere in space. And so a field is a function f, x, y, z that assigns a value to every point in space. All right, great. So really, what does that mean? It means, like, basically, let's just pretend we have ourselves a three-dimensional grid, right? We've got one direction this way, one direction that way, and one direction this way, right? And so a field could be just a bunch of numbers: 3, 5, 7, 8, 6, 2, 11, 15, 23, whatever. It's a whole bunch of numbers, a three-dimensional array of numbers. And if we take that into the physical world, then what we're talking about when we say space isn't just X, Y, Z space on a mathematical grid. We're actually talking about the real world, that we're going to be assigning some number to all of space, because the field doesn't just care where another charge is, it's going to fill up all of the space around a charge with numbers. And those numbers are going to look different. They're not going to be random. They're going to be defined by an equation. And that's the function f in this case. All right. Before we get too far into math, let's describe two types of fields. And you'll encounter both of these fields in this class and in future courses as well. Let's first talk about the scalar field. And the scalar field is the easier of the two fields we're going to talk about. It is just given by a function, again, describing, giving a numerical value to all space in x, y, z. And it just gives a single number. It gives a single number for each position. That's all it does. Now that number could have a unit associated with it. Maybe it has a physical meaning. We'll see. The more complicated of the fields is, of course, the vector field. Not that much harder, really, but harder, because not only does it give a number to every single position in space, but it's also going to give a direction to all of those as well. So it carries a number and direction for each position. Okay, cool. So guess which one is an electric field? Do you think an electric field is a scalar or a vector field? Of course, it is a vector field. The harder one, no doubt. We will do a scalar field a little bit later, but for now, we are talking about our vector field called the electric field. All right, so let's learn a little bit about this electric field beyond just theoretical background here. What are we actually talking about when we describe the electric field? Well, the electric field, first of all, is given by the capital letter E, and that E will give us a number in three-dimensional space, x, y, z, and it is described by a fairly simple equation. And I think that we can try to understand that equation in the following way. Let's give it a shot. We understand forces. We understand forces for these point charges very well. Again, I've got a charge here, positive, got another charge here, positive. It feels a force in that direction. It doesn't move, but it feels the force for now. The question is, all right, I know what the force on this charge is, but what is the electric field where it's located? Where's the electric field at that spot? Well, why don't we take it away? Why don't we take this charge away and see what's left over? What's here in this empty space? Well, there used to be a force when there was a charge there, but what if I take the force on the charge Q naught? Q naught is a designation for a test point charge. So I'm going to call this charge a test point charge. And the force on it is, let's pretend, something we know. We know how to calculate F. We know how to calculate the force on a point charge due to another charge. So I just pretend I know that. And so now I'm going to take that value and I'm going to remove the charge. In other words, I'm going to divide by Q naught. I'm going to divide by the charge that was feeling the force. So you take the force on the charge, and then you take the charge away by dividing it, and that's what the electric field is. That's a simple way for us to get the electric field. This equation is very unsatisfying. I put it there because it helps us understand how electric field and forces relate to one another, but it's not the equation I'm going to be using most of the time when I'm calculating electric field. But it's getting close. We're getting close to it. Q naught, as I said, is our test charge. And when you're doing test charges, you always make them positive. It's just a convention. But what we have with our test charges, it's going to help us to understand how an electric field works. And you'll see that in a second. F, as usual, is our force vector. And finally, E is the electric field vector. And so this E, for now, will be not just the, and by the way, I will write electric field as E field often. This is the E field at the point where Q naught lies. So we can only find the electric field right now where Q naught lies. So again, two charges, here's Q naught. We know the force on Q naught. If I divide the force on Q naught by Q naught, I have the electric field at that point. All right, so can I be more general? Can I calculate the electric field at other places? Well, yeah, and we can use this relationship of E equals F over Q naught to do it. Let's find out the electric field due to a single point charge. We'll start with what we know. We know that F is equal to K Q1 times Q2, but I'm going to write it as capital Q times Q naught. Just to differentiate between my Q's, where big Q is the one that is applying the force onto Q naught, which is feeling the force, our test charge. This is simply just Coulomb's law. Use a capital C. And then what we're doing is taking our E and applying the formula that E is equal to F divided by Q naught. If E equals F divided by Q naught, then this is equal to KQ over R squared R hat. That's it. We just get rid of the Q naught, and what's left over should be our electric field. Let me rewrite it at the top of the next page. Our electric field for a point charge, capital Q, is K, the Coulomb's constant, multiplied by capital Q, that's the one creating the electric field, multiplied by R. Now, typically R has been the distance between little q and big Q. That's not what R is now. R is the distance between big Q and wherever you want to find the electric field, whatever the distance away from Q you are. Q you are. Yeah, Q that you are. Okay, R hat. And there we go. That is our equation. And it is every bit as important as Coulomb's law. F equals KQ1 Q2 over R squared. In fact, I argue that this equation is more important. I just wanted to go back for a second and add our E equals F over Q naught equation a little more formally. We usually just see it as F equals, the force equals Q naught divided by E. You usually actually don't use this equation to get E, you usually get it to get F. And so for now on, let's stop thinking about the electric field as a consequence of taking a charge out. I want us to start thinking about the force as a consequence of putting a charge into a magnetic field. And so if I have some electric field, I said magnetic field, if I have some electric field, E equals KQ over R squared. I calculate that electric field at some distance R. Now I take a charged particle, a test charged particle, and I put it into the electric field Q naught. Now I actually know what the force on Q naught is. The force on Q naught is simply taking the electric field and multiplying by the charge gives me the force. And so these two equations here and here are going to prove very, very important for us when we deal with these point charges. And so we absolutely need to practice using this equation, this electric field equation, KQ over R squared. But before we can do that, we have to deal with the fact that it is a vector equation. It's going to have directions associated with it. And I was very comfortable with the directions associated with force equations because I knew that like charges repelled and unlike charges attracted one another. That helped me to figure out, in fact, it was necessary for me to figure out what the direction of the force is. But what is the direction of the electric field? If I have just some charge sitting there, and I'm looking for the electric field at this empty point over here, what is the direction of that electric field? I can calculate its magnitude using that equation, but how do I know which way the electric field goes? Okay, so let's talk about that. Let's talk about the direction of our electric field. Before we do that, just let me add to this equation what the various terms are because it is new for us. Of course, E we've defined already as the electric field. Let's call Q the charge creating electric field. Charge creating electric charge. So that is some electric charge. It is creating the electric field. And R, this time again, is not the distance between charges, but we're going to call it distance from Q to any point where we are trying to find electric field. All right, great. And we will come back to that equation, but let's talk about the directions of the electric field. Well, it turns out that once we know it, it's actually very easy to handle directions of electric fields, but we've got to figure out what it is. We've got to figure out which way the electric field points. And so the way we're going to do that is we're going to do a little experiment to figure out the directions of the E field. Let's start with a charge. We're going to start with a positive charge. This positive charge is our Q, and that Q is the one that is creating the electric field. And so the question is, what does the electric field look like? I don't know. I don't know what the electric field looks like. I can't see it. There's nothing around it. So what can we do? How can we measure the electric field? How can we measure the strength and direction of the electric field? Well, what we can do is we can put test charges in it. We can put test charges around it so that we can see what the reaction of those test charges is due to the electric field. Now this might seem circular, right? Like, am I really doing something? How am I detecting that electric field? I'm using charges to detect the electric field. Well, am I not just measuring the force? Yeah, you are. And so what we're going to do is we're going to take these Q naughts, these little test charges. We'll put one here. We'll put one on top of it. There's one. And we'll put one here too, but quite far away. All right, and we'll call them all Q naughts. All of the same size. And the question is, what is the force that those little Q naughts feel due to big Q? Well, since they're all positive, the reaction on our Q naught is that it's repulsed. It wants, or it feels, a force in this direction. This one feels a force in that direction. A little bit, let's make this a little smaller. Well, no, let's just make it big. It's fine. So we'll call that F. This one should also be about the same size, while this one will be far, far smaller because it's farther away. But in all cases, what we notice is, of course, that the force is in the direction away from our charge. It's going away from our positive charge. That's all the hint we need to figure out what the electric field is. Because the electric field is what is causing those forces. It's what is causing our test charges to move away. So in fact, those positive charges are tracing our electric field. We're going to define the electric field of a positive charge. I drew this squiggly line in between to indicate that my drawing is far, far away from the other one. They're not interacting with each other. But if I have a charge here and I want to draw the electric field around that charge, according to the test particles that I had, it should be going outwards. It should be going outwards from our Q. And please note, it should be happening in three-dimensional space, though I can't show it on this piece of paper. If you take that far positive charge over there and we put a charge in front of it, out here, then the electric field would have been coming out of the page. And so the same thing's going to happen for our plus Q behind me. We're going to draw all the electric field lines. But we're only going to be able to draw them in two-dimensional space. You're going to have to imagine the third dimension yourself, out of the page, into the page, and even like diagonal and stuff. There we go. And so that represents the electric field. That is our electric field. We used our test charges as kind of like tracers, right? They traced the direction of the electric field, but we know that that electric field isn't just occurring where our positive charges are, it's happening everywhere. It's happening everywhere, and so we can draw this electric field around it. And so now we know which way electric field lines go, such that if I had to find the electric field, let's say at this little dot right there, if I had to find it at that little dot that I drew, well, I know it's going away from the positive charge. And so I would draw the electric field like that. I would draw the electric field in the direction opposite the charge that's creating the electric field. Well, that's fine for a positive charge, but what happens in a negative charge? What are we going to get? The same situation? Let's go to the next page so we give ourselves plenty of room. And we'll make this a nice big negative charge. That is our capital Q. And we'll draw a couple of test charges around it. And what we know about these test charges are always positive, but now they are attracted to our capital Q. They're attracted to that negative charge. And so the direction of force is like so. And the length of the line also indicates the strength of the force itself. And what that indicates to me is that the electric field lines surrounding a negative charge actually go towards it, are actually going inwards as opposed to outwards. And we can draw that as well in the following way. We can take our negative Q here, and we can draw the electric field lines around it in the following way. This again is representing the electric field lines in all space when nothing else is around. And there we go. That is the electric field surrounding a negative charge. And we can also look at any individual place. If you weren't trying to draw the electric field of every place, and you just take, say, a random spot, let's say this one, let's do it in black. Say this one up here. Its electric field line at that spot, direction would be towards the negative, like so. And so all we've basically figured out as far as direction goes with electric fields is that the electric field direction is always away from a positive charge and always towards a negative charge. And we're going to use that information to build upon with our equation to solve for the electric field of not just one charge, but many charges.